Okay, I think we can slowly get started. Thank you all for attending today's virtual mini symposium. For those who don't know me, I'm Lukas Lindenroth. I'm a postdoctoral research fellow in the Surgical Robot Vision Group at WEISS under the lead of Professor Dan Stoyanov. This event is part of the WEISS Virtual Symposia series, which was originally an effort to bridge the unfortunately still ongoing COVID situation, but has been covering quite a few research fields since its start. For those who don't know us, WEISS is the Wellcome EPSRC Center for Interventional and Surgical Sciences here at University College London. We are a multidisciplinary research center spanning across departments from the Faculty of Engineering and the Faculty of Medical Sciences, which allows us to work in a very interdisciplinary research environment that is also, of course, highly collaborative. We are now around 150 researchers that spread across 20 research groups, which cover a wide range of healthcare-related research from biomedical optics and material science up to AI for medical imaging and robotic surgery. And of course, this also includes the theme of today's symposium, which is soft robotics in healthcare. Just to set the stage for our talks later on, even though soft robotics is as a field maturing quite a bit in recent times, you can see more and more soft robotic systems that are actually being applied in real world application scenarios. There are still various challenges which need to be addressed to make soft robots more and more viable, particularly for clinical settings. So this begins with the design of soft robots that are easily manufacturable and behave in a controllable manner, but it goes all the way up to control strategies for soft robots that are in complex interaction with the environment, for example, which in our case would be the patient. And of course, to make matters worse, in the case of soft robotics, all these aspects are all heavily intertwined. So in the first half of the afternoon, we will have a stronger focus on modeling and control of soft robots. But this does by no means mean that we won't hear about interesting design approaches, for example, and interesting systems overall. We'll have presentations by Dr. Moritz Becher of Disney Research, by Dr. Christian Duriez from INRIA, and Dr. Egidio Falotico from SSSA. Unfortunately, Christian can't be here today. However, he recorded a presentation for us, which we will then play later on. And just as a heads up, Christian kindly sent us two members of his great team at INRIA, Dr. Eulalie Kovot and Dr. Stefan Escada Navarro, will help later with answering questions on his behalf. In the second half, which will be chaired by my colleague, Dr. Agostino Stilli, we will focus more on design of soft robots. Ago, if you want to say a few words.
Yeah, thank you, Lucas, and hi, everybody. For those of you who don't know me, I am an assistant professor in medical physics in UCL. I'm also part of WEISS and the COI for robotics in the Surgical Robot Vision Group, led by Professor Stoyanov. And as Lucas mentioned, we are going to have a number of speakers in the second part of the workshop of the symposium, discussing design challenges in soft robotics for healthcare. We're going to have Dr. Sheila Russo, who is the director of the Material Robotics Lab and assistant professor at Boston University. Dr. George Mylonas, who is going to join us later on, director of the Harms Lab at Imperial College London, and also Dr. James Avery, also from the Harms Lab, who is a postdoc in the Harms Lab. And the last speaker is going to be Dr. Tommaso Ranzani, who is the PI of the Ranzani Lab at Boston University. And I guess at this point, I'll leave it to Lucas to move forward with the first part of the symposium.
Yes. If you have any questions at any point in time for the speakers, Feel free to use the Q&A function in Zoom. That's a bit easier to use than the chat function itself. So feel free to post your questions there, and then we will either address the questions after the presentations, or the speakers could reply to you in the chat, in the Q&A window. On another note, most of the talks today will be recorded. So if you want to rewind afterwards, you will most likely have the possibility. So without further ado, I'd like to introduce our first speaker. Dr. Moritz Becher is head of computational design and manufacturing at Disney Research, where he conducts some very impressive work into computational modeling to solve a wide range of problems. His talk today will revolve around design and control of soft robots using differential simulation. So the next speaker will be Christian Duriez, who is unfortunately not here today, as I mentioned earlier. He is the director of the defrost team at INRIA, which focuses on the design and control of soft robots, and particularly on haptic interaction. So Amy, if you wouldn't mind playing the video, that would be great.
Hi, thank you for inviting me in this workshop on soft robotics in healthcare. I will present today my work on unifying modeling of soft robots and soft tissues. This work has been done in collaboration with several people in my team, defrost, but in particularly with Egidio and Stefan Scuola. So why unifying model of soft robot and soft tissues? In fact, they have similar properties. High compliance, deformation with large displacement, and similar numerical models can be used. In interregional soft robotics, we would like to model and interact, to have model a contact and interaction between the model and its environment. In fact, when we want to drive a robot inside a soft environment, particularly when it interacts with soft tissue, imagine that we have a target on these soft tissues. Probably we may have some contact with these soft tissues, so it means that we need to integrate the model of deformation of soft tissues in the model of the soft robot. My background also reflects that unification. I've been working for several years on eye surgeries, on surgical simulation for training. For instance, here you see on this video the model of the eye made of a finite element model, and here you see more recently work on inverse model of the soft robot, also made of this FEM model computed in real time. So when we model soft bodies, I would say, for instance, here we want to model the liver. The first part is to have a constitutive equation. So we need to take some part of the soft tissues, do some tests to have the constitutive law, and create a numerical model. We often use in the team a FEM type of model. This FEM model will provide internal force deformations, and we add also some, we are using a lot constraint type of equation, Lagrange multiplier, to model contact and interaction. If we are considering dynamics, we need to add this part, which is the mass multiplied by the acceleration, and P is the known external force. If you think of a soft robot now, it's the same kind of equations. You still need a constitutive equation. So for instance, here we did some tests on silicon, and we also use a numerical model of the robot. We have the same thing, we compute the internal force, but for the constraint part, we can also use it to model the actuation, so cable or pressure. For the time integration, we often use time stepping method to model, to be able to be compatible with contact modeling. So instead, so as you may know, at the time of contact, the acceleration is not defined, so we prefer to use lower order integration scheme, which are using the difference of velocity instead of acceleration. And the time step is there, and here we use impulse instead of force. We perform one linearization per step. So here we have nonlinear deformations, and we have to linearize this deformation at every step of our simulation. So what you have to recall for the following is this matrix system, AX equal to B. So A is a known matrix, B is known vector, and you have to inverse the system to obtain X, the deformation, or the motion. It's the same kind of equation in the dynamic equations or in the quasi-static case. And you have the constraints here and here that appears in the equations. This formulation is completely compatible with rigid body dynamics. Actually, this time-stepping scheme has been taken in a paper dedicated to rigid body dynamics. So when we want to model interaction, we have to model the constraint, so we have to define some constraints. And we have here in the contact case two constraints, two different constraints. Either we are in contact and the distance between the object at the point of contact is 0, and then the force is positive. And the other case is that you have a non-null distance between the two objects, a positive distance between the two objects. And in that case, the force is 0. That's why we say that the Signorini law is a complementarity. There is two types of constraints. Either it's one of these cases or the other. We have the same kind of formulation for from the friction. So Coulomb's law is also a complementarity. We have two cases where either we are in the stick case, we have no relative displacement between the two objects in the tangential direction. And in that case, the tangential force, is strictly inside the curve. In the slip case, we have then a motion between the two objects, and the tangential force is strictly on the surface of the Coulomb's curve. With this type of constraints, we can extend, the type of constraints to model more and more complex interaction. So we can use, for instance, equality constraints to have a sliding or compute grasping. We can add new complementarity constraints to model, for instance, here the puncture or sliding friction, for instance, that you also see on this video. And here you see a video of a knot that you do for suturing. So in our framework, what is important is that, as you see, as you understand, you have the behavior of the deformable bodies of robots, and you have the constraint law. And in our framework, we have a way of constructing this matrix H that you see for the Lagrange multiplier, and their role is to link what's happening at the level of the motion of the nodes and what's happening at the level of the constraint. And that's the same thing for the robot. Here I put generalized coordinates for rigid robot, but you can also have different robot. The same thing. You have here the degrees of freedom of the robot, and you need to map these degrees of freedom to the constraint. So when you go in this direction, you impose positions. So for instance, the soft tissue impose the motion of the triangle model that is used for collision, and it drives the motion of the contact points. And when you are here, then you can compute the constraint law. And this constraint law gives you some force, some contact force, friction force, etc. And you have to map them back to the degrees of freedom of your object. So the force here on the contact points is distributed on the triangles of the object and on the here. It's the same thing here. It's more classical in this direction. In this, it's classical, I would say, in rigid robotics to transfer contact to define in the world coordinates to the generalized coordinate through the Jacobian matrix. And here, matrix H represents, in that case, the Jacobian of the robots. So now, how we handle these equations. So you imagine that you have a deformable robot in contact with a soft tissue. You have two deformable models for each of the two soft objects. And you have these Lagrange multipliers that we defined before. Now, what we will use in our tools is the show complements. So the show complement of this matrix system allows to compute actually the value of lambda, which is also something that is unknown. And to understand what is represent this show complement, I will give you this example of a soft table in contact with the floor. It's in fact W represents the mechanical coupling between the constraints. So in the table example, for instance, the four legs are discoupled, whereas here in that case the legs are coupled. And what you will find when you will compute this W matrix, this show complement, is a matrix here that is like uncoupled, with a diagonal block diagonal. So it means, so the size of this matrix is the number of contacts. Of course, if I have friction, I have 3 constraints per contact. So it will be, for instance, here 12 by 12 matrix, and here we will have blocks, 3 by 3 blocks that represent basically the contacts of the 4 legs. And in that case, the 4 contacts are discoupled, where here the 4 friction contacts are coupled by the small coupling that we have between the legs. And it's really important when you solve that, because in that case, you will find some, the solution is that we are in a slip case, as here we are in the stick case. There are 2 issues to compute this W matrix: is the size of the A matrix, because we have to inverse or pseudo inverse this matrix, and the size of H. And now, what's happening when we want to control a robot with contact? So first, how we control the robot? For that, we use inverse deformable model. And for this inverse deformable model, we will also use these show complements, this compliance in constraint space. So basically, let me take a static model of the robot to make it simple. Here I have the stiffness matrix of my model. So it's a big matrix that gives the stiffness on my hand. And instead of using the contact here, I'm using another kind of constraints for the cable and for the effector. So for the cable, imagine that you have a cable that goes through the structure. You can say that lambda is the pulling force, but as you know the pulling force, you know the distribution of the force on all the objects that are on all the points on which the cable goes through. Okay, so you can create 1 constraint per cable. So for instance, here we have a robot with 8 cables, so we will have 8 constraints. And at the tip of the robot, we will define 3 supplementarity constraints that represent the n vector. So these constraints, in that case, H matrix is really simple. It's a basically matrix with full of 0, except at the nodes that is concerned, and where you have the identity matrix on this node. And basically what you have here is the coupling between the two. So when you put a force of 1 on one of this cable, you have directly through this matrix the motion that it will create on the n effector. So here it's a very small matrix, it's a 3 by 8 matrix that represents the coupling between the actuators and the effector. And basically, if you want to inverse the model, if you want to drive this n effector motion, so you want to drive it, so you want to impose a displacement. For that, you need to minimize the actual n effector position compared to the desired position. And so we minimize, and you can do that in a quadratic form. And in that case, this is a quadratic programming problem, a classical quadratic program. You have solvers to calculate that, and you can easily solve them using classical solvers. And what we have done, and that was a little bit more tricky, is to be able to inverse the model with contact. And in that case, what was more difficult is to combine this inverse model, okay, plus the complementarity constraints that are due to the contact. But we end up with a solution where we were able to find a solution for the solver to have what we solve a QPCC quadratic problem with complementarity constraints. And in this example, you see that if we do not model in the inverse problem the obstacle, we have a difference between the position, so what should be the inverse model of the robot and what's in practice. But if we are able to track the obstacle and model its behavior, you will see that we will be able to integrate the contact in the inverse model. That's what we do here. Here we model the obstacle in the simulation. You see that computed contacts are found between the robot and the obstacle, and we are able to change basically the control of the robot, to adapt the control of the robot, the inverse model, to really reach the target here, even if there are some contacts. We can use this also to do some contact force measurement. So if we imagine to have a camera with a measure of the position of this point, okay, we can also use this inverse problem thanks to the measurement we are doing. And in that case, we can add basically new constraints for the force that we could apply on the robot. And basically the inverse problem finds the external force we are applying on the robot. So the same kind of equations. When we push on the robot, we see that we can also inverse the problem and find the force that are applied in the robot. We have combined that with other type of sensor. For instance, here we are using capacitive sensor to find where the user is pushing on the touchpad. We can use also this capacitive sensor on the soft finger here. You cannot see them, but they are placed on the finger. And with the capacitive sensor, we know where the user is applying some force. And we have also pressure air measurement. And in that case, so there is no control with camera, etc. It's only based on the airflow, so it's not pressure, it's airflow measurement plus capacitive sensor. And we integrate that with the model to find the force that is applied on the robot. So we can transform the robot and made it act as a force sensor. So an example of application of mixing this soft robot and soft tissue models is this Bartolo project that we do in collaboration with Falotico. It's a robotized prostate biopsy. So we have the soft tissue that are modeled based on the MRI, and you can see the deformation of the tissue. This model with FEM also. And you can see also that when we deform the organ, we can also deform the image. And basically, here it's not a soft robot, but it's a rigid robot equipped with a soft part here. It's a soft cylinder. It's a kind of soft robot because this part is soft. What we really want to do is to inverse a model to really be able to put to do the biopsy exactly where we want. So we put a target of the biopsy on the prostate. Here you see the target, and we use the inverse model to really align the probe just in face of the target. And if we move the target, the robot will automatically adapt its position in the inverse problem. And now we are working also on how to optimize the design, in particular sensing, to basically this problem of soft robot in contact with its environment. So thank you for your attention, and now Elodie and Stefan can answer your questions. Bye-bye, thank you.
Thank you, Amy. And yeah, another welcome to Stefan and Eulalie. Thank you so much for being here. I think there are no questions in the chat yet, so I will start. Basically, just to pick up our discussion about sensing and to take it a step forward. So if you're now simulating a whole anatomical environment with your patient anatomy and the software world and everything interacting, this becomes very, very tricky to sense in reality, right? So there are two ways of approaching this. Either you're trying to reconstruct the whole scene and try to make everything as accurate as possible, or you try to focus on the important bits. So on your actuation, on the degrees of freedom that actually matter for your task requirements in the end. What do you think? Where should this research head? Where's this research going? Do you think you would have to have entirely distributed sensing across the whole robot? Do you think it would be enough to just sense in the actuator space of the robot? What are your takes on this?
Okay, that's a good question. I think I need a second to think about the I think if you're thinking about the real patient, then the problem is really the registration. So of the relevant portion of the relevant organs and so on that are being affected by the operation. And so I think that in that case you have sensing that's more visual, I would say, or marker based or feature based on the visuals, because you cannot necessarily intervene the patient with, you cannot put, maybe, at least to the degree I know, it's more difficult to put some sensors inside the patient to track. So that would mean, but I think if you track the region of interest, in this case of the patient, then the other scope, at least for now, you can skip, I think, in terms of modeling, like the different mobility and so on. Maybe you can have something on the background modeling, let's say respiration or something that could help. But yeah, and from the robot side, I think it's possible to continue using the traditional methods for sensing, like force torque sensing on the end effector or in the tool. Yeah, I don't know if Eulalie thinks has some some comments.
Yeah, I think you answered well. I agree with what you said.
Great. Yeah, I think it would probably be very, very tricky to do that in real time inside a patient and ensure stability of your controller and whatnot at the same time. So it probably makes sense to just focus on the bits that are important. Right?
But we are, or from my personal perspective, also I'm very interested in proprioception and so on, and what Moritz was talking about, sensor models that basically allow us to compute the sensor output from the deformation that is of our objects, or in the inverse case, finding force distributions that will explain observed sensor values. And so we think that with this we can build anatomical soft robots, meaning that would be more for training than for the real intervention, but that could even basically simulate an intervention with patient-specific data, patient-specific geometry, or even patient-specific phantoms, so that we can test the intervention beforehand, study it before going to the real use case. Or if we have a robotics supported intervention, we have on the one side the phantom that is modeling how the organ is being affected by the intervention, and the robotic system, we can verify that it's doing the correct thing. the correct procedure in terms of the plan. So that's the kind of perspective we have on this now. I think outside of the group, the other people working with SOFA have focused more on things like, for instance, tracking the actual organ position of the real patients and so on.
So basically, pre-operative planning would be the way to go, because you can play around. You can ensure you don't have to worry that your controller stability just goes through the roof suddenly.
Yes,
and these kind of things.
Yes, I think that would be a means to verify that, if especially in automated interventions, that you would, I guess, more execute a pre-planned intervention that with smaller adjustments, that you, when you have verified, then trying to be super adapted to in terms of sensing to the real patient.
And in terms of haptics, how, so this is probably very, very subjective, but how realistic do these simulations feel like? I have personally never tried it out so far on a haptic device. I don't know, like how much influence do the faster dynamics of the system have, and how does the computation time come into play there? Did you ever run any user studies or something along amongst clinicians or something along those lines?
So yeah, unfortunately, my experience is not very large in this area.
Yeah, me neither. Sorry.
No worries. I mean, it looks fantastic, and I mean, from a static or quasi-static perspective, this is probably more than you can ever hope for. I'm just wondering, like, because also these haptic devices on their own do not feel super realistic, despite forces possibly being transmitted accurately. So for me personally, I always have this bit of hurdle with haptics, and I always find it a bit tricky to have an abstract view on that. Cool. Okay, if we have no other questions, then I would like to thank you both very much for joining us here.
Yeah, thank you. Thank you for having us.
And then we will move on to our last speaker of the first session. So this would be Dr. Egidio Falotico, who is an assistant professor at the Biorobotics Institute as SSSA in Pisa, whereas he's heading the brain-inspired robotics laboratory. So his research involves, amongst other incredible fields such as neurorobotics, learning-based control strategies for soft continuum robots, and this is what we'll be talking about today.
Yeah, thank you, Lukas, for the introduction, and thanks for inviting me. This is really an amazing symposium. So let me share my presentation. Okay. I hope that everybody can see it.
Yes, all good.
Good, thank you. Okay, so today we are going to talk about the learning-based controller for soft continuum robots. I mean, soft and continuum robots are now being developed for several applications, as you have already seen in previous presentation. And you may see here a couple of examples from an octopus arm, part of the octopus robot, or the STIFLOP surgical manipulator. But of course, these robots have very interesting capabilities, but at the same time, if we look at them from a control point of view, of course, they present great challenges for the control. In particular, this is because, of course, these are hyper-redundant structures which are extremely adaptable to the environment, but at the same time, they are very difficult to model due to the under-actuation that they present. In addition to this, the actuators that usually are embedded in this platform can control only few among of the infinite possible joint formation. Of course, there are models, as also shown in previous presentation, that try to be used for the control of these robots, and models goes from a more static one that include constant curvature or piecewise constant curvature to models that, of course, try to take also into consideration the dynamics like the Coursera rod or the FEM models. Of course, this also implies an increase in the computational complexity and accuracy. For this reason, since this difficulty in modeling, we decided to actually try to follow another path for the control of this kind of robots, that is try to use learning-based approaches. And I'll try to show him in this presentation what we have actually achieved in this. So why we believe that learning-based approach can be an optimal solution for the control of this kind of robots. In particular, if we look at the different space from a control point of view that we have for the control of this kind of robots, so starting from the actuation space, moving through joint space and configuration space, where you have, for example, the arc parameters, and finally you can get the position and orientation of the end effector. So of course, all this space may require transformation that can be quite expensive from a computational point of view. So we tried actually to create a kind of direct mapping between the actuation space and task space. And I'm going to present the results for controllers that are static or dynamics. Let's start from what we consider a kind of seminal works. This was a work done by our lab in 2015, and the idea was to try to make a comparison between more, let's say, classic robotic approach, a Jacobian-based inverse static controller, and another one which was based on a feed-forward neural network, a simple neural network that could learn the mapping between the end effector position and the cable tension. Of course, here we consider for the robot a model of the octopus arm. And it was interested in the results. What we get is that, of course, in simulation, the Jacobian model was way more accurate. But when we moved on the real robot, of course, due to uncertainty also in the manufacturing, what happened is that the Jacobian method had some error, and the feed-forward neural network performed better for the control of this kind of robot. After this, we actually moved and we were part of this European project called iSupport, whose goal was to actually support mainly elderly or impaired people in the bathing task. The idea is, of course, to provide people help during for example, the showering. And in the project, two main robotic platforms were developed. A motorized chair that was used in order to help the subject during the shower, and also a soft robotic arm that was used for pouring the water and detergent, but also for wiping and scrubbing. Our group worked, of course, on the design of the soft robotic shower arm. And this was the solution that we proposed. So we had this robot, which was composed of 3 modules, as you can see, and had also the possibility to have an exchangeable end effectors according to the task that was supposed to be done by the robot itself. As said, we have 3 identical modules, and each module is provided of 2 kinds of actuation. It has pneumatic chambers, 3 pairs of pneumatic chambers in particular, and also cables. So the joint effect of cable and pneumatics could actually allow to regulate the stiffness of the robot. So as a first solution for the control of this robot, we come out with a a new neural network, the idea was to, of course, to control the robot from a kinematic point of view. So we extended the previous work that I showed done on the octopus arm, and we made this new neural network, which is again a feed-forward neural network. But what we added was actually we tried to learn a new mapping between the input and the output neural network. In particular, here we considered also not only the current configuration of the actuation space, but we also considered the current and the previous configuration of the end effector space. And of course, the idea is that the neural network could provide the next configuration for the actuation space. So actually, in a way, it's learning the differential inverse kinematic model. And actually, we are able with this neural network to control the two modules of our robot, as you can see, and doing different tasks from line following, but also we demonstrate that it was possible to do disturbance rejection when actually we moved the robot, and this was possible because actually we used a feedback based on a magnetic sensor. We also demonstrate the capability of the robot to following with obstacles, but this was mainly done by the morphological properties of the robot itself. And we also extended the controller in order to consider, for example, also the orientation. So as you can see here, the robot is able to follow a line in space by keeping the orientation fixed. We actually extended this model since we were supposed also to have an interaction with the subject when, for example, we want to perform the scrubbing task. So the idea here was to actually control not only the position, but also the stiffness. In order to do this, what we did was to propose a new learning algorithm that in this case is based on a reinforcement learning that could actually doing and performing a multi optimization, so as more objectives, not only the position, but can also optimize the stiffness. So this means that we could find for the same position the configuration of the robot which had greater stiffness thanks to this reward matrix that we gave to the reinforcement learning algorithm. And here, actually, one of the trials that we performed, you see, for example, the task here was the washing one, where the robot was controlled, and we also integrated our controller based on the neural network with a visual system, and that allowed the robot, for example, to follow the movement of the subject during the task itself. After this, we realized that, okay, now we were able to control our robot, to use that for kinematics control, but of course we wanted to extend this in order also to exploit more the capability of the robot from a dynamic point of view. For this reason, we started thinking how we could design a dynamic controller, and to do this, we followed a specific approach. We started from learning the forward dynamic model of the robot. This means that we were able to learn a mapping between the actuation at current state and the position and the velocity of our robot. And we were able, for example, to predict what was the acceleration. We discretized the model, and this allowed for a recursive mapping where we actually used previous values of the end effector position in order to predict the next state of our robot. This was possible thanks to the implementation of a recurrent neural network that you can see here, where we actually backpropagate the value predicted by neural network itself in order to get an estimation of the previous values of the end effector position. We actually set up also induce a trajectory optimization method for open loop control, and actually we use the classic traditional trajectory optimization method that is based on sequential quadratic programming. And with this method, actually, we applied, this method directly on the neural network that we derived from the robot itself. So we could actually, thanks to this, generate the trajectory at actuation level that could allow, for example, to follow a path at the end effector level. So, of course, when we consider the dynamic workspace of the robot with respect to the static one, it increased a lot, since now we also have the inertia during the movement, and this allowed the robot to have a bigger end effector space. This also allowed to reduce the time that was needed for the sampling, because since it is moving in a dynamic way, the sampling in this case took only a few minutes to collect the needed data in order to learn the forward model. And here you can see, for example, on the left, the sampling, how we just move in a random way the robot to let him explore the environment. And here after the learning part and after applying the optimization, we were able, for example, to generate a circular task or a spiral one, just changing the trajectory that was provided and let the optimization method computing the new trajectory at the actuation level. What we found out was also that actually when we implemented this model, we discovered that thanks to the compliant viscosity of the soft manipulators, there are specific attractors that could be used for developing high stable and open loop controller. As you can see here in the video, when we disturb the robot, even if the controller is in open loop, it is able to actually go back to the initial trajectory, the circular one, without any feedback to the robot. So this means that this is a self-stabilizing property of the robot itself. We actually applied our model in order also to study the biological system. And in particular, what we did and what we actually discovered was that we applied our reaching model based on the dynamic controller, as that you can see here on the right part of the slide, on a simulated octopus arm. And what we discover is that we get the same tangential band propagation velocity profile that was actually found in the real octopus. So we started wondering how this was possible, in the sense that since we did not apply a bi-inspired control, so we actually decided to change several configurations in our simulation. So, for example, we changed the body stiffness, we modified the density of the medium to understand what was actually making that invariant profile. And what we found out is that when we actually modify the stiffness, or we modify, for example, the density of the medium, the invariant profile is no longer there. So that disappears, but this does not happen, for example, if we change the configuration of the robot, when, for example, we use 4 actuators instead than 3, or only 2 actuators and the base instead than 3. So actually what we derived for this was that are the morphological and environmental properties that affects the observed invariant profile. So let me conclude my presentation. What I can say is that, of course, model-free approaches so far demonstrate to be a suitable solution for the control of soft continuum system. And I believe that for manipulation in a structural environment, which should be, for example, the next step for the next natural step if we consider that, of course, now we developed different models, but we had not real interaction with the environment, we still believe that model-free methods can show promising results. Of course, also an hybrid approach that could actually use model-free and model-based could be really an interesting line of research, since also the model-based approaches are now becoming more robust. And in the end, I want to go back to the last work that I showed, where we actually tried to replicate animal strategies. And I do believe that we should try to get a better understanding on these strategies are made in order to generate more elegant strategies also for the control of soft robot. So let me acknowledge also my group and the different projects that supported this research, and I would thank you for your attention.
Thank you so much, Egidio. That was really, really impressive. Particularly the results from your dynamic model were really, really good. So if you now think about translating that into use cases, into applications, or into clinical procedures, how do you ensure that nothing goes wrong in the real world? Like, how do you make your controller safe, and how do you again ensure stability when you're performing procedures that are dangerous to a patient, for example?
Yeah, I mean, of course, the dynamic approach is more attractive, but maybe it's not mature enough for this kind of application. Of course, I would suggest now to rely on, let's say, static or quasi-static models, which are more robust and maybe also more suitable for this kind of application.
So go slow and be safe that way. That's, I guess that's a good way of handling that. We have one question from the audience, from Keshav. Really interesting work. How sample efficient was your training for your various learning models? Did you have to utilize any simulation training data?
No, actually, the idea of using learning is because actually we could directly learn from the robot what we have done so far. So using this motor bubbling approach, where we let the robot exploring the environment, is demonstrated to be very powerful, because we could collect easily the data and directly learn from the robot without the use of simulation. Of course, I'm not saying that we do not rely on simulation, because before all the tests on the real robot, we work on simulators, because of course we need that to understand if our controllers are suitable before moving on the real platform.
And maybe simulation then helps going the next step, like you said, in the end, then becoming more and more complicated and taking into account more and more complicated scenes in the end.
Yeah.
I think if we don't have any more questions, we would move on to the next session, because we're slightly behind schedule. Huge thank you again, Egidio. That was really cool. And I'm handing over to Ago.
Thank you, Lukas. And yes, as Lukas mentioned, we are running a little bit late. So without any further ado, let me introduce Dr. Sheila Russo, assistant professor at Boston University and director of the Material Robotics Lab. Dr. Russo's background is at the intersection of biomedical robotics, soft robotics, advanced manufacturing, and advanced materials technologies. And her research focuses on design and development and fabrication of biocompatible, smart, soft, and miniaturized surgical robots that could help restore sense and feedback and distal dexterity in minimal invasive procedures. Thank you, Sheila, for joining us today, and I'll leave it to you.
Thank you, Ago, for the introduction. Thanks, everybody, for having me and inviting me to the symposium. It's my pleasure to be here, really excited.
So today I'm going to be talking to you about soft robots for advanced interventional endoscopy, and in particular, of course, about the research that we have going on in the material robotics lab at Boston University. We are working on the design, manufacturing, materials of soft, multi-scale biomedical robotic systems. And one of the main motivation actually that we are working on this area is to tackle challenges that are presented by minimal invasive surgical procedures. So basically, if you're not really familiar with what they are, we're mostly targeting endoscopic surgical procedures, so flexible endoscopy. These procedures are, as you can see here, very different with respect to more traditional open surgery or laparoscopic surgery, because instruments are very flexible. They can be inserted inside natural orifices. So think about navigating inside your lungs by passing through your nostrils, or in your stomach by inserting the endoscope through the mouth of the patient. And so, of course, they are presenting huge advantages with respect to, less trauma, less hospitalization, and so more advantages for the patient. But at the same time, they do present more complexity for surgeons, and so learning curves in order to basically be trained to use these instruments and use them to not only perform diagnosis, but also surgical technique, surgical tasks and therapy. That does require a long learning curve. And these instruments are typically have poor distal dexterity and sensor feedback. So in this scenario, really, I think this scenario is really motivating us roboticists, because it's really a challenging environment to navigate. It's not structured. It is a delicate environment. If you do something wrong, you could potentially harm tissue, healthy tissue, or organs. And so these kinds of applications are really what gets us up in the morning out of bed, because we are interested and excited about solving fundamental challenges in robotics that are associated with this scenario, such as how do we perform safe navigation? How do we build a robot that can have distal articulation and sensing embedded and is still safe for this specific, really challenging scenario? And so how also do we embed materials in the robot that can avoid harm to the tissues, that are biocompatible or hemocompatible, and so on and so forth? And so I don't have to tell you that soft robots are really a promising technology in medicine and in surgery. There has been, this slide is of course non-exhaustive. There have been a variety of different examples of soft robots for surgery, laparoscopic surgery, cardiovascular procedures, and so on and so forth. And the research community is getting really excited about these tools and how to scale them down, miniaturize them to navigate in really challenging areas of the human body, such as the cardiovascular system or the brain or the lungs, and so on and so forth. And the great thing about these robots is that, of course, they are made out of soft materials, which are almost the same sort, which have almost the same sort of compliance as human skin. And so you can immediately understand why those would be really beneficial when it comes to interacting with a human body or a patient. So in my lab, our approach is combining different research areas at the interface between surgical robotics and soft robotics, of course, together with microrobotics and origami-inspired robotic mechanisms. And we'll see in a second why. And we are really interested on the mechanical side of these robots. And so we are basically developing advanced manufacturing technologies in our lab to build these innovative soft robotic systems. And today I want to highlight two classes of soft robots that we are working on, and those are hybrid soft foldable robots. And so you can see here the interaction, the interface between soft robotics and origami-inspired robotics, and soft reactive robotic skins. So we will start with hybrid soft foldable robots, and I'll tell you a little bit about what they are. These robots are basically trying to combine the best of both worlds when it comes to soft fluidic actuation, which is safe inside the human body because the robot does not use any sort of like electrical inputs. There are no motors, no rigid components, and there is soft fluids that can be used to pressurize the chambers of the robots. So think about saline solution, for example, that could be applied, which is safe inside the human body. And of course, they also have those soft materials that which we have seen are really safe. But they also combine the advantages of origami-inspired rigid robotic systems. And so that means that these robots can be folded down in really compact configurations, and they can take really small amount of space. And so they can, for example, be mounted around commercially available medical instrumentation. Think about catheters, endoscopes, navigate inside a complex anatomy safely. And then once you reach the surgical target area, these robots can unfold and deploy at the surgical target and perform some significant surgical tasks, such as, for example, remove tissue, remove a tumor, perform a biopsy, and so on and so forth. And these are some examples of the robots that the hybrid soft foldable robots that we have developed, but today I'm mostly going to be focusing on this system right here, which is a robotic manipulator that can be added on to colonoscopes for early stage cancer removal in the gastrointestinal tract. And this is just an overview of the manufacturing paradigm that we have developed for building these systems. And so we are basically first manufacturing soft micro-robotic actuators out of soft lithography and laser precision micromachining. So combining these two techniques to build biocompatible soft micro-robotic actuators out of materials that can be safe, that are safe inside the human body. And then we take these soft fluidic micro-robotic actuators and we use a process that is called chemical surface modification to bond soft materials together with hard materials, and a variety of hard materials can be used in this process, such as plastics and metals, conductive materials and non-conductive materials, and so on. And we basically create a sort of a sandwich of layers of materials, 2D layers. And then out of this sandwich, we can basically, once again, laser cut our robotic actuators, and they look like this. And I want to stress here how thin and small you can manufacture these. Think about, for example, integrating this outside of an endoscope or passing that through a working channel of a catheter and things like that, and navigating inside, for example, a deep-seated tumor in the brain. And so even though they can be manufactured pretty small, their force and torque and mechanical performance can be tuned, and they are actually much better performing than their fully soft micro robotic actuator counterparts. And that's the best, and that's combining the best of these technologies, because basically you can tune the force that the robot can develop at its tip, but you can also tune the deflection that these robotic system can have, and so sort of like predict a little bit better how the robot is going to be moving, pre-engineer the range of movement that you're going to be needing depending on a specific surgical procedure that you want to perform, and so on and so forth. And also the nice thing is that you can pre-engineer where those rigid components will be integrated inside the robot, or you can move them around by using actuators so that you can tune the stiffness of these soft foldable robotic systems. Another really interesting thing is that of course, sensing is really important in robotics, and it's even more important when you are thinking about inserting a robot inside the human body to perform surgery. You want to know where you are, you want to know what you're doing with a robot, and potentially you want to have some sort of haptic feedback to make sure that the interaction between the robot and the tissue, the biological tissue that you are interacting with, is safe. And so in this example here, I'm showing that we have embedded conductive traces and conductive plates just by simply playing around with the materials that we can embed in our manufacturing strategy. And we have created a capacitive sensor. So when these soft microfluidic actuator is inflating, these two conductive plates can basically create this capacitive effect, and we can measure the bending angle of this specific end effector. But you could use this, for example, also to, again, monitor the interaction, the update with haptic feedback that you're having with tissue. I won't go too much into the technical details, but we have analytically modeled these systems both from their mechanical performance and also from their sensing performance specifically. And if you are curious a little bit about that, I would recommend go check our paper in Advanced Material Technologies to learn a little bit more about that. But basically, once we had developed these systems, we asked ourselves, okay, what can we do with that really? What could they be used for? And so we reached out to our clinical collaborator at Brigham and Women's Hospital here in Boston, and we went in his lab in the OR, and we started, shadowing him in the OR and in his lab, performing ex vivo tests to basically understand some of the specifications of a minimally invasive surgical procedure for early stage cancer removal in the gastrointestinal tract. And so we instrumented his tools with sensors and so on to measure workspace that is necessary in this kind of procedures and forces and so on. And we engineered a solution to this problem, because basically endoscopes don't have, as I said, distal dexterity and sensor feedback and so on. And so we augmented the capabilities of the colonoscope by creating an add-on, so mounting a soft foldable robotic arm around the periphery of the colonoscope to add 3 degrees of freedom and manipulation capabilities of tissue such that we could perform biopsies, tissue removal. And this is an ex vivo test, which means that we have used porcine stomach to basically validate our platform. And here you can see that the robot that is mounted around a colonoscope is basically grasping onto tissue. We have a miniaturized vacuum-based soft gripper at the tip of the robotic arm as end effector. And when we apply vacuum, basically the system is able to retract tissue, which means pulling the tissue up such that we could then go through the working channel of the colonoscope and basically remove this part of the tissue where we are basically saying, oh, if there was a lesion here, we could then remove it and analyze it in case this was a cancerous lesion. So switching gears to the second part of the talk, I'd like to talk about soft reactive skins and what these are. They're basically, think about sleeves or skins that could be manufactured really thin, and you could mount them around already existing medical instrumentation to augment, again, the capabilities of colonoscopes or catheters or other traditional rigid tools that are used in surgery. And these skins are have a combination of sensors and actuators such that they can be reactive. And so they can return haptic feedback to the surgeon, telling them how much force they are exerting onto tissue, and then potentially deploy soft actuators to lower those forces down. And so this is particularly useful in a scenario such as colonoscopy, where because patients are typically sedated, there is no sort of return haptic feedback or return for novice surgeons, especially that they are learning the procedure. And so because it's so hard to navigate inside the colon with a colonoscope that has only 2 degrees of freedom, sometimes surgeons push too hard and apply too high forces onto those tissues, as you can see here. And that can basically create in postoperative, at the postoperative stage, perforations, bleeding, and a sort of a variety of other complications that are present, especially with patients that have already comorbidities. And so we engineered a solution where we are mounting a soft robotic skin around the colonoscope that has to be really thin in order not to augment the diameter of the system, of course, too much. And it has soft optical sensors that can detect these high forces and automatically deploy a sort of like airbag that can help with the navigation of the system and advancing the colonoscope in the colon up until the cecum, which is the last segment of the colon. And this is just an overview, a quick video showing you how the system works. So you have those soft optical sensors, and as you press onto them, these soft robotic actuators will deploy. We have created a simple graphic user interface for our clinical collaborator to use, through which they can control the inflation or deflation of those soft robotic actuators, so that they can, if they deem it necessary, they can deploy them to help with navigation tasks at any time. And also they can monitor the pressure inserted inside the robotic actuators and the force that is, of course, monitored by the sensors. We have designed the system by using finite element analysis modeling. So we have basically created a model of our robot in order to make sure that the deployment of those soft actuators would not interfere with the sensing, and making sure that the distribution between the skin, within the skin of the robot, of those actuators and sensors was properly designed. And we also investigated how much forces that soft robotic sleeve would impart onto colon, and how these forces can be lowered down with our system with respect to a traditional colonoscope. So this is just the way that the system is fabricated, the way that the robot is fabricated. As you can see, it's simple pouring and casting of silicone elastomers, and the soft optical sensors are embedded by simply injecting different materials that have different refractive indices, such that you can guide light through the soft robotic sleeve. And this is particularly useful because, again, there is no high voltage or high current in this sensing methodology, so it's completely safe to be used inside the human body. We have, of course, calibrated our sensors, making sure that they responded specifically to the force inputs that we are interested in. As you can imagine, the sleeve is bending together with the colonoscope inside the colon. So we wanted to make sure specifically for this application that our system was able to monitor only force interactions between the colonoscope and the colon, but potentially you could use it as well for bending sensing, because it's responsive for that as well. So we calibrated the system, created an algorithm that would allow us to filter the inputs that we are not interested in measuring. And also we characterize our soft actuators embedded in the sleeve to make sure that they would be able to apply the forces in the range that is necessary to provide an easier navigation inside the colon. And this is just a quick video to show you that the system is basically responsive to force inputs rather than bending. You can see how it can pretty accurately estimate the force input that we are imparting on it. And this is an in vitro validation that we have done with a colon simulator. This is a thermoplastic elastomer TPE bag that we have created simulating the colon. The benefit of this is that it's transparent and clear, so that you can see our system mounted around a colonoscope. And in here, the physician is basically navigating with a colonoscope inside, and as they do navigate, they will press onto a wall of the colon, pretty much what happens in colonoscopy. And the system is capable, as you can see here, to inflate our soft robotic actuators when it senses too much force is exerted, and continue navigation. At the same time, we wanted to quantitatively measure these forces that are exerted. And so here you see we have 3 force sensors. Those are pads that we mounted inside our colonoscope model. And we were able to monitor how much force is exerted when the sleeve is non-active. So 4.7 Newton concentrated in one sensor, which means in just one location of the column. And that, again, can potentially be harmful. And so when the robot senses that, it'll deploy our robotic actuators and distribute the force around a larger area, as you can see here. So just want to conclude by, again, highlighting these 2 classes of soft robotic system for surgery, hybrid soft foldable robotic systems, and soft reactive robotic skins, and really highlight the fact that the applications that we're working in surgery and medicine, they are really exciting because they, as roboticists, they really provide us with the possibility of solving open challenges in robotics, such as, again, how do we perform safe navigation? How do we embed distal articulation and integrated sensing? And how do we create systems that can actually, even if they are soft, can actually provide effective force transmission in surgical applications? And these surgical applications, I believe, are really more challenging than other sort of applications. But at the same time, they are really motivating because at the end of the day, you're building a novel surgical tool that can potentially be on the market in 5 or 10 years from now, potentially solve problems and create novel surgical procedures that are not possible to perform today, or perform them in a better way with respect to what is currently done these days. And our main goals are, to create systems that are easy to use. They don't disrupt surgical workflow. They are easy, cheap to be integrated in our scenario, and they can be disposable, single-use robots. And so I just want to conclude by thanking the members of the lab and our funding agencies. And thank you, of course, for your attention. I'd really be happy to take any questions.
Thank you very much, Sheila. Very interesting work. And this was definitely a great overview about it. I think we also got a mixed question in our Q&A, highlighting the great panorama offered by your presentation. And definitely origami-inspired robotics there seems to offer a very effective solution to complex manufacturing problems that we face in soft robotics, especially to increase repeatability. We all know that soft robotics started almost on the crafting side of our research, and getting repeatability there and being able to integrate reliably sensing elements is of paramount importance. So in this context, I guess I can start with a question. How did you balance in your research your distributing sensing elements with the real estate in your robotic system and with vision-based sensing, which is obviously one of the main tools we use in surgical robotics?
Yeah, that's a really good question. We are actually working on some other systems that I wasn't able to show today because they're still under review, so stay tuned for that. We are embedding also vision sensing into these soft robots as well. It's really one of the most, I guess, preferred ways of navigation for surgeons, because they have direct visual feedback of the surgical target area, and that's really important for performing diagnosis and therapy. I think there is a balance between what kind of sensors you want to integrate inside the systems and what is necessary from a clinical perspective. So we are really in trying to have a constant conversation with our clinical collaborators in order to tackle that issue and understand what they need. And of course, we're trying to balance that with what roboticists are interested in. And so what kind of sensors we are also interested in developing. I don't know if that answers your question, but.
Yeah, thank you very much, Sheila. And indeed, I agree. The communication with clinicians in this context, they being one of the most important things to exercise during these design developments. We get a couple of questions. Got one in the chat from Manios. Very impressive work. Are the force transmission capabilities of the foldable pop-up robot enough to employ traditional surgical grippers, such as cutters or forceps?
Yeah, so the gripper that we integrated in the robot is soft. We haven't yet integrated a traditional rigid surgical gripper. However, I would say the weight of those, especially if you sort of like customize them, we have the ability in the lab to manufacture our own grippers and out of traditional stainless steel materials like 316L and things like that. We're looking into that as well. So we are rather, again, manufacturing those specific tools and customizing them to mount on our robots rather than just using maybe something off the shelf that is already available. We prefer that just because it is typically a way, the way that those surgical graspers are actuated is by cable. So cable-driven actuation, you would need to pull that cable, and the integration of those in our soft foldable systems would be less effective. But we have combined these, the soft foldable robotic arm together with, for example, electrocautery device tools to make sure that that would be compatible, passing the surgical electrocautery device through the working channel of the colonoscope, for example, and having the arm outside of the colonoscope, grasping the tissue, pulling the tissue up, and working with the electrocautery device and knife to cut the tissue. So there are definitely a lot of open opportunities in that scenario. The forces that the soft foldable robots can exert, you can tune them, and we have seen a range from, like, I want to say 50 millinewtons up to until almost 1 Newton. So theoretically, yes, the answer to your question is it could be possible.
Thank you very much, Sheila. I guess we should probably move forward because we are running already a bit late. So I will now introduce you Dr. George Mylonas, who is now with us. And George is the director of the HARMS lab at Imperial College London. And today is going to present together with Dr. James Avery, who is a postdoctoral research associate in the HARMS lab. And I leave it to you, George.
Many thanks, Agostino, and many thanks, Lukas, both of you, to invite us. And also thanks to Sheila, who in fact covered a lot of ground of things that I would probably present during my talk, but this will help us probably to save a little bit of time because I don't need to include them anyway, to mention anyway. So this talk is about, is basically is a personal account, is how we see soft medical robotics and how the need for medical robots, soft medical robots, grew organically through a necessity. I mean, we had a problem, we had a need, and then this led us to develop soft robots. And I'm very happy to share this virtual podium with my good friend and colleague, James Avery, who's a research fellow with the Hamlin Center. So that's the talk outline here. First, a few things about our need, why a soft medical robot, then the learning curve. We learn soft robotics as much as we learn soft robotics the hard way, and you will see why. And the solutions. Necessity, as I said, is the mother of invention, and hopefully this will become apparent on how and why we evolve soft robots and why we came up with these solutions. So one of the first needs, one of the first requirements for us was to break away from conventional approaches to like this one, this continuum manipulator, to actuate surgical instruments. Because as you engineers know, that these are suffering a number of limitations, like they don't exert high forces, very limited traction forces, suffer from poor controllability, resolution, and repeatability, and also they're not very easily reconfigurable if you wanted, for instance, to reconfigure them online during the operation. So in a paradigm shift, we proposed to use, instead of a continuum manipulator, a parallel manipulator. So you can see that, which is a very simple project, a very simple concept. It's not something that we invented, but with a few modifications, we made it ours. And in fact, we filed a patent on this concept. So basically what we have here, we have this quasi-static peripheral scaffold. It can be rigid, quasi-rigid, so not quasi-static, rigid or semi-rigid peripheral scaffold with a number of entry points, which allow us to insert a number of cables. In this case, we have 4 cables, which allow us to control this instrument in 3 degrees of freedom. As you know, you can only pull with cables, so you lose 1 degree of freedom there. And the good thing about this kind of approach is that it's intrinsically very good. I mean, it can provide you with very high resolution and repeatability, very high traction forces, and is easily reconfigurable and simple and cheap. And if you have more cables, in this case, you have, for instance, 6 cables, you can introduce 5 degrees of freedom of movement of this end effector. And this can be used as an overtube, basically, as an accommodating tube to accommodate any off-the-shelf flexible instruments you may have in the hospital. And this answers one of the questions asked by the audience earlier. Yes, we are able to do that. So this is it. This is the very first prototype. You can see pretty much is like controlling a string puppet. What you see here on the left is the master manipulator connected with some almost invisible fishing lines to slave instrument there. So your hand movements are effortlessly translated into movements of your end effector on the other end. So the next need was, okay, we have this nice system. This parallel manipulator is very good, but how do we use it? How do we insert it inside the body? How do we use it alongside other instruments which you may have in your hospital? And this brings us to the endoscope that Sheila mentioned earlier. The flexible endoscope by itself doesn't do much. It's basically used for endoscopic navigation, for diagnosis, and very limited manipulation of the tissue. You have to be Japanese, for instance, if you want to perform something more advanced like endoscopic submucosal dissection, for instance, which involves bimanual dexterity. So our need was to find a way of deploying these little manipulators in front of the endoscope and controlling them externally by a set of motors sitting on the other end outside the patient. We use this yellow, shown in yellow here. These are force transmission conduits, also known as Bowden cables. You might be familiar by this name. So these Bowden cables are used to control the length of these cables, which in turn control the overtubes, which in turn can control any introduced flexible instruments you may have at the hospital, which you can insert them through the biopsy channels. There are endoscopes with 1 or 2 biopsy channels, but also easily, probably more preferably, you can insert them from the outside of the endoscope, from the side of the endoscope. So now the next problem was, how do we come up with a design that allow us to have a quasi-rigid scaffold, a platform that will support these cables, but also at the same time is not big, it's small enough to be inserted through a natural orifice, and then when inside the body, then you can deploy it so you can actually perform the operation. And the solution naturally came that this could be an inflatable. This is the soft component of the system. So the idea is that we have this inflatable attachment to any endoscope you may have available. Then it is also disposable because it's cheap. So you put it around the endoscope, you inflate it, you are able to control the length of the cables using the motors outside the patient, and then you're off to go and do the operation. There is a patent on this, as I said, and also this technology has been now licensed a couple of years ago to a company in Singapore. So this brings us to the hard way, which I mentioned in the beginning of the talk, how we discovered our way of, coming up with soft robotics, basically soft mechanisms, the hard way. You can see here, the need was to come up with the scaffold, the soft scaffold. And initially we started with a couple of layers actually of latex rings that we weld together using latex glue. And then we sandwich them in between ripstop material. And then I had to spend a few days at the haberdashery shop in John Lewis and maybe a couple of other places, talking to old women looking for their own things, for embroidery hoops, for instance. And from that, you develop the tools. So we can show this and then remove the excess material and glue together these 4 different little components, this like a donut shaped inflatable components. So this made it work, basically, made the job. So allow us to move from this very first prototype, generation 1, to a system which gives by manual dexterity to a flexible endoscope, as you can see here on the bottom left, but is still rigid, and then allow us to come up with a soft design, which when inflated allows you to control the surgical instruments. Here you can see on the left, you see a grasper being controlled by this parallel manipulator. And on the right, you can see the diathermy. You can see the bimanual dexterity offered by the system. And the amount of forces you can exert with this kind of mechanism is phenomenal. I mean, we've been able to exert something like a 70 Newton inside the body in certain axes of the end effector. But the problem was that although we learned the hard way how to do some kind of robotics, soft robotics, this still wasn't enough, which means that this design was very big, was really unreliable. When you inflate it, you use it for, I don't know, a couple of times, and then it's gone, it's burst. So because we wanted to perform animal trials, we wanted to go and try the system in a pig trial. First of all, we didn't want to sacrifice an animal for nothing, just to go there and the system wouldn't work, or it would burst halfway through. And secondly, it was very expensive. It was something like £6,000 to do the animal trial in Northwick Park. So we came up with an intermediate solution just to prove the concept, the principle. We think this kind of, on the top right, you can see this deployable structure, but of course is rigid. So it's by no means compatible with the soft tissue. Nevertheless, we've been able to introduce it inside the body, inside the pig, to maintain pneumorectum, and we did part of this ESD procedure, as you can see on the right. So because we wanted to find an easier way, basically, to come up with our soft mechanisms, we thought of developing a system that will allow us to weld together several layers of plastic films. And Mark Runciman, who's now writing up for his PhD, he came up with this nice robotic welding mechanism there on the left, which basically what you can do with this, you can take a layer of plastic. Usually this is a sandwich of PE, PET, PE, because PE is a thermoplastic material and PET is the one which provides the strength of this film. And then when you heat it up, then it will melt, obviously, and then you can weld it with the several other films. So basically, you can take this film, spray it with some infrared absorbing liquid that will heat up locally when you shine the laser through it. This is infrared laser at 25 watt, I think, laser diode. Then you can make your shape. You can design it in a CAD. You can embed some other mechanisms, some other components, like this electrodes, for instance, and you will see later why we embed electrodes inside this kind of components. Then we put another layer of plastic, we laser weld it, and then another layer of plastic with a different shape. In this case, this is the actuation package over the sensing package. You weld it again, and basically you have some kind of soft finger robotic end effector. You trim off the material, and that's it. You're off. And you can see the details on this paper down here. And you can do things like more complicated shapes. Here you can see like 14 layers of plastic welded on top of the other. Well, it's not that simple. I mean, it takes a little bit of fiddling around, some masking involved, but it is possible. So, and it's very cheap and very quick. And this allowed us to come up with this design. Now, the old Cyclops on the top left, they're very unreliable and big and taking ages to put together. And then here you can see another version of the system where you can see on this simulator of the colon, insert it from through the rectum all the way to the cecum. The system is popping out, and then you inflate it. And with this, Mark has been able to, and our clinical collaborator with Mark has been able to perform this ESD procedure, endoscopic submucosal dissection, and easily, very quickly remove this 2 centimeters of tissue from this chicken thigh. But now, the next problem was, okay, we were talking about soft robots, and this is something which is good, it works, but it's not fully soft. And also Bowden cables are, as all of you know, they're suffering from a number of limitations. One being that if you go through a curve, then the model will change, and then there is friction and all sorts of things taking place there. So can we come up with something which will be fully soft and it will be better? Can we embed it, for instance, inside the body? Soft actuation in a way. So what we did, what Mark did, he basically took one step further. These pouch motors introduced on this paper you can see here by Niyama. And instead of using a pneumatic actuation, we're using hydraulic actuation. He optimized the design, and he very easily tried very different designs using the laser welding. He didn't have to use any CNC or any other like a more time-consuming approaches. And he showed that you can control the position of this very accurately and repeatably, the position of this actuator, the contraction of the actuator, simply based on pressure and the volume of the liquid we inject in it. And this is evident from this graph with a yellow line showing the root square error in open loop actuation. And this brings us to the more latest of the designs. We're using now 3 of these hydraulically actuated pouch motors. We can control, as you can see, this end effector. We have a fourth degree of freedom, a third degree of freedom actuated by pushing hydraulically this end effector in and out. You will see further down the video. And also now, not just the actuation, but also the scaffold which supports the tendons, as you can see here on the right, is all made in a soft component. So it's a pop-up robot, basically. You weld it in a very short period of time, and then you insert it inside the body, and then actuation and support of the tendons is happening in situ. And on this very graphic image here, I will stop, and I will ask my colleague James to carry on with the talk. James, are you there?
James, I'm afraid we cannot hear you. Don't know if you have a problem with the mic.
How about now?
All good.
Yeah,
there you go.
Zoom defaulted to the wrong device. Sorry about that.
No
So can you all see my screen?
Yes.
Fantastic. Yeah, so like George, I came to soft robotics the hard way. So I was in medical physics at UCL before. So I'm a medical physicist or a biomedical engineer rather than a soft roboticist. But yeah, so the task we're trying to solve with this work is trying to add some closed loop control to these devices. So, and in order to do that, we need the sensing, and we all know why we need the sensing, but the limitations, especially for the typical soft robotic sensing solutions in MIS context, are that we need multiple degrees of freedom, particularly if we have these complicated pop-up robots. And we don't want to compromise the material properties, and we also don't want to compromise the collapsibility or the deployability. So large, bulky silicon rubber things don't really cut it. And then we also have the issue of biocompatibility. So like if we wanted to add carbon nanotubes or whatever into the device, that gives us a limitation as well. So the solution we came up with in consultation with George, basically, I think it might have been one of our first ever meetings that we had when I joined, was that we were talking about integrating electrodes into these hydraulic chambers in these pop-up devices. And by taking multiple impedance measurements between all of these electrodes, we can build up a map of the conductivity changes inside, and then give a kind of a map of the shape change. And the benefit of this is that it's low profile. So all we're doing is adding thin wires inside the device, and we're adding them inside. So we're basically not changing the profile particularly too much. And that also means we don't affect the deployability. So we can still have them the same pop-up structures as before. So how we actually do this is we use frequency division multiplexed EIT, but EIT means make images of impedance. So we have electrodes embedded in these pop-up finger electrodes, for example, and we optimize the injection patterns. Basically, we choose where we want to inject current between in those devices. And then, so we inject across the whole thing, but also between the hinges. And then during actuation, we measure the voltage on every single electrode at different frequencies. So we get a full picture as we demodulate each individual electrode at different frequencies separately, means we can get each measurement is then sensitive to different things. So by we only have one inlet, but we're able to sense the changes in the bending just by choosing which electrodes we inject between. So here we can see unfortunately the videos have come out of sync. If I say it once, they're out of sync. So but unfortunately, so we can see the bending mode. So the voltages are changing in the bending, but they're not changing too much when we're changing just the cross section. So this way we're able to separate out the changes in that single chamber by choosing which electrodes we interrogate. But we can actually go beyond this. We can reconstruct images. So by having a finite element model of our actuator, so here we have it in its resting, kind of inflated but resting state. By knowing the geometry and the position of the electrodes, we can build up a conductivity map and a sensitivity map. So on the left, the white regions are where that particular measurement combination is sensitive to. So if you look at the middle, the red one, by selecting the measurements on the left-hand side, we're only sensitive to the bending angle on the left. So when we bend angle 1, the red one doesn't change. But when we bend angle 2, the red one does change. So that shows we can choose where we're sensitive to. And by combining all of these separate measurements up into a sensitivity map, we do the typical inversion. And we can get a map of the conductivity change. And we can see on the bottom right there, we see like as the each angle is moving separately, we get a image of the apparent conductivity change in each at each stage. And these changes they appear as apparent conductivity changes, but they're distinct for each bending mode. And the benefit of this is we can get a full map throughout the chamber. And we can also pick out different regions of activity that we're interested in. And we get, with the current implementation, we have 50 Hertz frame rate, and the results show they're very repeatable. In fact, the data is more repeatable, the sensing is more repeatable and the imaging is more repeatable than the actual actuator. And all of this is added, this can all be done in real time, just by adding some, the only complexity is really the manufacturing and the wiring. So it doesn't necessarily just have to be fully hydraulic. We also have an example of say a retractor, where we have a pneumatic beam, which is and then pops up and stiffens, and then we by inflating the bending chamber with the electrodes in it, we cause it to retract and to bend. So we can actually have these hybrid designs, and we have a repeatable voltage change during the retraction. But also, it doesn't have to be boring plain beams too. It can also be something much more complicated. So here we have a pterodactyl which flaps, and we give Terry the pterodactyl a backpack, and we can actually reconstruct localized deformations. So this you can actually see on the edges of the wings. You can see as the wings are compressing, as the wing is flapping upwards. It's difficult to see. It's a perennial problem, isn't it, with clear plastics. But as the wing are bending up, the edges are deforming and squeezing. And also you can see like the spine in the middle, which is where we have in the middle of Terry to make him flap. So you can actually look at these individual regions. And the idea for this is then these are uncalibrated measures at the beginning. These are apparent conductivity changes rather than strictly speaking directly reconstructing the shape. So work is ongoing on developing classifiers to convert this into control variables, but also and deciding whether it's the voltages or whether picking out the images themselves is ongoing. So that's where we are at the moment. And thanks very much for the opportunity to talk. Thanks for George for letting me, and thanks for inviting me.
Thank you very much, James. And thank you very much, George, as well. Very interesting presentation, impressive work. And clearly, I see how the retrofitting of standard robotic surgical tools can provide faster pathways for soft robotics technology to be translated into clinical scenario. And this is obviously something we all struggle with in the context of soft robotics research. And I believe that this is the way we should pursue in that sense. And I just wanted to ask you from my side before moving to questions in the Q&A, looking at your work on the Cyclops system, given that we are looking into similar challenges. How important is in your scenario to control the roughness of the surface of your soft interface when it comes to interaction with soft tissue?
Well, I guess it depends on the tissue to start with. And when we're talking about the colon, the rectum, this is something which is quite sensitive. And first of all, one aspect is pain for the patient, and the other one is you don't want to cause any damage, any abrasion or this kind of thing. So I think it's quite important, and you can use silicone for this. So you can use some harder mechanisms, harder designs, and then dress them up in some kind of softer skin. But this is not ideal. So a fully soft mechanism basically is quite necessary. I don't know if this answers your question.
Thank you, George. Then I guess from the audience, I guess the question there is, with your manufacturing process for your multi-layer system, how small can you go, and in terms of manufacturing and controllability of your system, and if it can be used to seal?
Yeah, I mean, you can come up with any design you want, basically. So you can use it for sealing as well. Yes. Probably what this question is referring to is when you cross between different lumens, if you want to seal one lumen with respect to the other, for instance, for nodes. And this is a possibility, yes. As long as what you're trying to weld together is thermoplastic, so you can actually weld it together, then I don't see any limitations to this. In terms of size, again, this depends on the type of materials you're using, what kind of plastic you're using, the thickness of the plastic, of course, the laser and the collimator you're using, how big is the spot you're gonna create to laser weld. But theoretically, there's no limit to what you want to do. And for instance, one of the smallest designs we come up is about 35 millimeter in diameter in terms of a scaffold. So miniaturization is not necessarily an issue. Of course, if you go to the micro scale, I guess, then there might be some other issues, but we've not looked into such a small scale so far using this approach.
Thank you very much, George. Don't think we have any more questions from the audience. Lukas, do you have any questions from your side?
I have a question for James, actually. Can you envision a way of integrating your sensing technology into more traditional soft robotic manipulators, like, for example, soft continuum manipulators? Do you think that would be a way to achieve contact sensing or something along those lines?
I think so. I mean, so the argument for using the EIT in this context is that we're looking at doing hydraulic devices but other conductive mediums could be used. Like, so there are examples of using it like with conductive silicons and things like that. So in theory, it's just a case of getting the electrodes in the device. So, but those are, I mean, we're not materials experts, but we should probably talk to people that are. But making conductive silicons is, and that still have the properties that you want for soft robotics is not trivial. But in theory, it's the difficult part is getting the electrodes in. So I think we're trying to explore things like that and try and find some low-hanging fruit to see what's usable. But I think for sure, maybe like a conductive sheath or something like that might be a way to go. For sure.
If you don't mind adding, in fact, we're working with the Chinese University of Hong Kong, TUM, and Johns Hopkins on a joint project on exactly what Lukas you just mentioned.
Cool.
It's just early days, so I mean, basically we just started and we just got a few PhDs to work on this.
Fantastic.
Great.
Thank you.
Well, thank you very much, George, and thank you very much, James. I guess we should move forward because we are not getting any better with our delay. So I'll now introduce our last speaker, Dr. Tommaso Ranzani, assistant professor at Boston University and director of the Ranzani Lab. And Tommaso, I'll leave it to you at this point.
Thanks, Agostino. And thanks for inviting me, for you and Luke for inviting me. It's been a really fun workshop so far. I'm really enjoying it. And great speakers so far. I think a lot of the things that have been told are a good segue to what I'm going to be talking about. So as George just said before, it's going to help some of the flow here. But anyway, so I started my own lab at Boston University a couple of years ago. Part of mechanical engineering, also with the biomedical engineering and material science division, and the lab is the morphable biorobotics lab. And what I'm going to be talking about today is a little bit of some of perspectives of the challenges and approaches that we're using to develop to enable more complex, more dexterous soft biomedical devices that are actually able to perform complex surgeries at the level of current instrumentations. And so, and I want to start a little bit from the top. So the research, the main research field that we're working on is soft robotics. And I think one of the aspects I wanted to highlight about the soft robotic field is the fact that it brought back the attention within the robot to the body of the robot. Okay, so for a long time, the body is sort of been a kind of something you can buy and you can implement your control algorithms on. While with soft robotic field brought back the attention to the fact that the body can actually add fundamental features to the functionality of the robot itself. It can enable the robot to be inherently safe in manipulating it, more robust in manipulating, able to reconfigure its body, able to resist mechanical damage. Okay? And all these new opportunities are very exciting. And if we're talking about medical application, the sort of like key aspect, and that we've also heard today from a lot of you, is can be seen as compliance matching. So we can really match the compliance of the robot with the tissue, and we can build inherently safe machines. And those inherently safe machines, they can safely be wear, they can be in intimate contact with the tissue without damaging it, they can navigate within the body without damaging it. And so my experience in trying to apply some of design principles from the soft robotic field into medical application started with laparoscopic applications. Okay, so if you think about laparoscopic applications, you have a very you start from very simple instrument, straight instrument, rigid tool, rigid stick with a grasp at the tip. Can't get simpler than that. But despite this, medical doctors make really amazing stuff with these very simple instrumentations. And the idea here of this very first project I started working on was, why don't we try to create something that has a similar level of complexity as, for example, the octopus tentacle, and try to introduce that level of complexity into a surgical instruments? What kind of functionalities, what would that enable from a medical point of view? And that led actually to learning a lot of things. So going from a scenario where you have this very rigid, simple, straight tool and you basically perform your operation just by controlling the very tip of it, to having an instrument that can be can have multiple functionality within the same structure. So you can use part of the manipulator to, for example, perform retraction, and use this compliance matching, use this safe interaction with the tissue to actually use multiple components of the instrument at the same time, and then use maybe the distal part to perform a grasping task, a distal manipulation task. You can use this increased dexterity to reach areas that would be otherwise very complicated to be reached with a simple rigid instrumentation, or you can use a selective stiffening mechanism to decouple the tasks that can be performed at different locations of the arm. And you can see we demonstrated this with very simple scenarios. We use like this kind of sort of compliant tissues that were just inflated balloons, and try to show with basically no control, just by using the dexterity and the properties of the robot, we're able to manipulate these compliant organs very easily, completely open loop. We can use variable stiffness structures embedded within the manipulator to tune how much force we're applying to objects. And so there's a lot of, we started seeing a lot of the potential that can be extracted from using soft robotic technologies in medicine. What we're now particularly interested, especially in my lab, and it's based a lot of the lessons that we've learned from this, is not only we are we can exploit the fact that those robots are inherently safe in the interaction with the tissues, but we can actually exploit that interaction with the tissues, and we can really use that to create instruments that outperform current instrumentation. The first thing. The second thing is we can really, again, embed the principle of soft robotics, so creating more complex, how more complex bodies result in more complex functionalities, and thus really be able to enable additional functionalities to be embedded on soft surgical systems. And so with respect to the first part, if you think about, so we were working on this sort of inflatable soft actuators. We've been working on that for some time now. And the idea is very similar to actually what George Mylonas presented before. So you basically bond selectively subsequent layers of thermoplastic elastomers. In this case, we're using thermoplastic elastomers, very thin ones. Those are 100 micron layer thick. And we're using Teflon layers, so sometimes Teflon splay works as well, just to shield the parts where you don't want to bond. And you can easily create these structures that are initially almost take no space, and then can inflate to pre-programmed motions. They can extend, they can bend, they can have multi-degree of freedom structures that can come out. And the advantage here is that because you're not actually stretching a polymer, the behavior that they have is very linear, right? So you're just inflating basically a bag that has a predefined shape. So makes the control a lot easier, actually. And you can use them, I said before, bracing is one of the key aspects, right? So you can use them to locally brace, locally provide stability at the distal end of a flexible instrument, for example. And that result, if you look at the plot at the top, for example, in being able to really restore force transmission at the very tip. One of the things that you typically lose in flexible instrumentations is that as you get further and further away from the entry axis, you lose a lot of the stiffness required to perform effective manipulation. You may be able to restore dexterity, but being able then to apply forces if you don't have bracing, if you don't have anchoring, it's very hard to be performed. And this is a very, very simple and effective way that we found working very, very well in restoring stiffening at the very tip of the endoscope. And we can get even a step further where you can have something that is mounted on the endoscope and just dump it there at the location. And if the video starts, yeah. And again, we're using bracing again. So you see those two areas. We are bracing to the floor of an ex vivo tissue, and then you have a soft grasper that lifts the tissue up. And by virtue of the counter traction provided by the two points and the central grasper, you can very easily lift up the tissue, and then you can remove the lesion. And having something deployable actually makes it even easier, because at that point, you're not even more constrained by the degrees of freedom of the endoscope, right? So you can use the endoscope to position this object wherever you want, and you would just lift the tissue up and just cut it out and keep going round and round until you perform a full resection of your lesion. Again, this is particularly helpful also to maintain a good visualization of the surgical target during the procedure. And so that's sort of the first advantage, the first direction we're going towards in the lab. So like being able to exploit more and more bracing, safe contact, not just avoiding harm to surrounding tissues, but to really using that anchoring, that bracing to perform more effectively your task. The second part that we're looking at is, if we want our soft robot to do more complex tasks, we need to equip them with more degrees of freedom, more complexity, and more functionalities. And this means creating more complex soft robotic bodies. And creating more complex soft robotic bodies is ultimately a manufacturing challenge. Okay, so again, a lot of your previous presentation were sort of a segue to this. Give me a good segue to this, because manufacturing is really hard, and creating manufacturing processes allow you to create multi-scale features and multiple different materials. Having something that is three-dimensional provides complexity within it. It's very hard. And the step right after that I'll hint at the end of the presentation is Well, as soon as you realize that, the second problem that hands you back is how you can actually control the level of complexity that you struggled so much to be able to integrate that. And then we're working a little bit on that as well. So starting with the manufacturing, we are working on a combination of two-dimensional processes. So we use lithographic processes, which have been widely adopted. If you think about soft robotic devices, a lot of soft robotic devices use soft lithographic based methods from centimeter to micro scale. It's a very well-known technique, working very well, and well known, especially from the field of microfluidics. We combined it with laser micromachining. We have a very accurate laser micromachining system with a 16 micron accuracy that allow us to sort of combine the shape of the chambers that you have in your inflatable actuators that are designed through the lithographic process with the laser cutting process that you can sort of cut around to create sort of different behavior of these soft micro actuators. So you can create continuous bending, discrete bending, you create twisting just by playing around how the material is deposited around the actuator and how the actuator is designed. And you can get even a step a little bit further than this. So soft actuator bends because one side is thinner than the other. That's how most of them work, at least. We can actually program the 3D motion a little bit better using this laser micromachining system because we can cut so close to the side of the actuator so that the thinnest membrane is not necessarily the one on top, but could be the one on the side. And once it's the one on the side, it means it will bend in plane. So you can see here in the in plane motion, the side membrane of the actuator becomes the thinnest one. So when you pressurize it, it will bend in plane. And that means that typical soft lithographic processes are designed to create out of plane kind of motion, but with this laser micromachining process, we're able to tune the bending plane and to pre-design that independently on the fact that we're constrained by a 2D manufacturing process. And we can, of course, create even in between motion. The second thing is that laser micromachining and soft lithography are inherently 2D processes. And we're able to transform that into a 3D manufacturing processes by using, instead of water or air as a pressurizing fluid, by using a curable material to be cured inside. And we tested a lot of different materials. Here are listed some of them that we're working fairly well. We can use like stiffer material, we can use softer materials, we can use materials that have the same compliance as the actuator itself. But the idea is that you inject it, you create the desired deformation, and then you sort of freeze that configuration, freeze the tridimensional shape. And if you've added a stiffer material, you've now created a composite that has parts stiffer, parts softer material. If you inserted a softer material, you've now softened the properties of your device. So you can really tune the mechanics here quite a lot. But of course, I've been talking about complexity. These are just simple microactuators. So like, how can we use this process to create really complex devices? And to sort of demonstrate that, I liked before the idea of the pterodactyl. That was a good one. We choose a spider in this case. And because it's a very small animal, has a lot of different degrees of freedom, has definitely a three-dimensional shape, and we took it as a challenge to say, if we can manufacture this, we can at least demonstrate that we can manufacture very complex structures. And this is what we come up with. This is based on a peacock spider, which is an Australian spider. It's very small, has a lot of degrees of freedom, and within this design, there are a lot of different aspects that we wanted to demonstrate. So you see here, you have the legs here, and the legs are initially fabricated flat, but then injected with material that is cured and is keeping them in the three-dimensional shape. And in this way, you create the joints. Okay, so once you have created the joints, you can actuate the joints with another actuator that is on bottom, that is here highlighted in blue. And then you have similarly the head that is sort of like inflated and keep it as it is. And on top of that, there are microfluidic channels that are rearranged on top of this spherical dome to change the shape. And the abdomen here, that is, I think it's a 7 layer, if I remember correctly, microfluidic, three-dimensional microfluidic circuit that have all microfluidic channels passing through it. And you can see here some of the functionalities here. So you start all flat. Videos on top and bottom show kind of all the different degrees of freedom that can be actuated at different time. DNA color patterning. So here we're passing the fluid through the different layers, across the different layers. This is again a 3-dimensional microfluidic circuit, all based on a 2D manufacturing process. We can actuate all these different degrees of freedom. We can really sort of like showcase all the level of complexity that we can integrate in this very, very small device. And just to sort of like highlight some of the features of the complexity that we're able to do here. So we have 12 layers. It's an 18mm device with a minimum feature size of 40 micron. We can go lower than 40 micron. That depends on the kind of clean room that you're using. With the 7 structural degrees of freedom, structural means the things that you inject with the material that then you can cure inside. Not that you have to, but those what we choose for this specific design. 9 degrees of freedom, and it's entirely biocompatible. So there's no adhesive. All the materials used here are entirely biocompatible, can be implanted with no harm, and embed some of the features of microfluidics as well. However, one of the challenges, as soon as we sort of like fabricated this, we immediately realized, and that was based on the challenge of making those videos that I showed before, is that each of these degree of freedom right now was controlled manually. So what you could not see there was me and my colleagues behind the doors with a lot of syringe trying to sort of like move things around and make sure everything was kind of moving properly and things like that. And this is, of course, it's one step forward, right? So you cannot have everything all at the same time. But it sort of highlighted the challenge, saying, okay, now we have the technology to create all this complexity. Now let's try to find methods to manage that. And this leads to the last part, the last topic that I wanted to talk about, that is how we can actually embed onboard control. And this could be a little bit confusing for some of the control people. So with onboard control, I really think about physically handling all the different fluidic lines that are embedded within the soft robot, okay, not high level control. And the way we're exploring right now in my lab is by using, again, a fluid approach. So we're using fluids to create 3-dimensional structures. We're using fluid to actuate. Why not using fluids to control? Okay, and we're using a specific class of fluids. Again, those are biocompatible. Again, they're magnetorological fluids. We synthesize them in the lab together with our collaborator. And they're basically an aqueous solution of ferric particles and water. And the magnetorological fluids, what they do is basically, as soon as you expose them to a magnetic field, they increase their yield strength and they behave as a solid. Okay? And you see here some of the characterization. They're very well known. Modeling is very well known, very predictable. Nothing new from that side. What is interesting is how you can actually integrate them into for controlling a multi-degree of freedom soft robot. So you can think about having a continuously recirculating flow of MR fluid within your robot. And as you have a continuously recirculating fluid, you have your normal pressure drop within your robotic system. But as soon as you apply your magnetic field, the magnetic field causes a pressure drop to happen within your actuator, which causes actuation. And you can see here, so you have continuously flowing, we have a peristaltic pump here, then we get a magnetic field there, causes pressure drop, you have actuation. Very simple. We can generate the magnetic field in any way you want. We use permanent magnet here because it's easier. You can use electropermanent magnet, you can use electromagnet, you can use external magnetic field, you can use any way you want. It's very straightforward. But it works very well. So as soon as you apply the magnetic field, you have an instantaneous generation of a pressure drop. And the interesting thing is that you can scale this to multiple degrees of freedom. Okay, so at this point, we build this very simple structure where we have 4 different branches. Each of them, its resistance can be tuned based on the magnetic field. And by just adjusting the value of the magnetic field across those different 4 branches, you can independently control each of the 2 actuators or both of them at the same time. Okay? So for those of you who like the electronic analogy, I have here the sort of the electronic scheme here, where the capacitors are the actuators and the resistors are the 4 branches of the fluid. And we're scaling this even further to a 5 degree of freedom robot in this case. So in this case, again, the same principle. So you have only 1 input, 1 output for 5 degree of freedom. It's continuously recirculating the fluid here. And my PhD student got really skilled at positioning on the fly the magnetic field appropriately. But the interesting thing is that you can basically, depending on the configuration of the magnetic field, you can selectively activate whatever degree of freedom you want. Okay? So you can selectively activate any one independently, any combination of them very, very repeatedly. And again, the fluid is biocompatible. The process is very scalable. We're actually working on scaling this down and integrating at the level of sort of the spider scale. There's still a few hiccups to work through, but we're getting there. And that's mostly what I want to talk about. So like really highlighting some of the advantages in terms of bracing and creating more complex soft robotic systems to enable more complex soft surgical devices. And I'd like to conclude by thanking the amazing group of people I've had the pleasure to work with. It's wonderful to see the group growing over these last years. Acknowledge, of course, the fundings, and thank you again for inviting me to this workshop.
Thank you very much, Tommaso. Great presentation, and really enjoyed it. How we go in soft robotics from using bioinspiration in the design to biomimetics for validation. It's a very broad spectrum we usually cover there, and clearly a very big component of material science behind all of the research you presented. And it's great to see how we are at the intersection of micromachining and basically working on the material side and chemical side, basically.
Yeah, it's interesting to see like how soft robotics is forcing everyone to learn almost everything, and forcing you to collaborate with people from all different backgrounds. I think it's one of the greatest aspects of this field.
Yeah, definitely pushing the limit of robotics in that sense in the context of cross-disciplinarity. I just wanted to just go back a bit to your experience in the context of surgical robotics and the use of soft robotic system in this context. So do you think that the right paradigm there for soft robotics is considering this system as disposable single-use system, or in the future you foresee this moving towards more sterilizable systems that can be reused in the context of clinical operations?
Well, that's a really good question. So I'm very tempted to start saying that the going towards disposable would be easier, because and would sort of be a good initial step, because we can optimize the processes, and I think a lot of these layer by layer manufacturing processes is quite well suited to translate into like industrial settings and towards commercially viable devices. And so those are going to be very cheap, very fast to be fabricated. I'm not sure how well durable they're going to be. Okay, so I feel like those could be extremely valuable, mostly as disposable devices. I think before we can prove that there is something that can be used for a large number of uses reliably, clinically, there is still a lot of work to be done from the material point of view and guaranteeing that that's going to happen. And if you think about it, like the Da Vinci itself, right? So the instrument of the Da Vinci, because they're of course concerned about wear of the cables in the tools, they reduce a lot the allowed use of the tools, right? And that's of course conservative. So we don't want to sort of like push this with soft robotic systems, because they exploit, of course, deformation. They tend to exploit a lot the interaction of the tissue with the robot itself. So I would say mechanical damage is quite likely to happen. So
what's in your experience on that scale, the fatigue effect on your robotic system? How far did you push your systems in terms of resistance to fatigue on that scale?
So for the layer by layer systems, I think they're very strong. So I still have prototypes from 2016, and they're still working. I mean, I didn't run a fatigue test, right? So they're not being continued working, right? So but they're still working, and haven't seen any change in the performance. For the silicon based, yeah, that's very different. I would say that's going to be very different. But in that case, you of course training the polymer. So from actuation point of view, probably we're going hundreds of cycles, maybe. That would be a reasonable end of life for the device.
Sounds really good. I don't see any further question in the Q&A section. Lukas, do you have any question from your side, or do we have any other questions from the speakers?
I just raised my hand the moment you said that.
Sorry.
No, just a very quick question at the end. When is the magnetorheological fluid going into an MRI?
Oh, that's a good point. That's a good point. I don't think so.
No?
I don't think it will. But that's a good point. That's not something we've been looking at yet, because the clinical applications we're looking at do not require that so far. Okay. But that's actually a very good point. I haven't thought about it.
I mean, it would fit perfectly, especially because you can scale it to such an extreme extent. You can go very, very small. So I guess it might be something.
Yeah, that's
definitely
an interesting
conversation to have here.
Yeah. Anyway, just on the side.
Yeah, that actually would be interesting to talk about that, because we're working a lot with a lot of other collaborators on optimizing those fluids, optimizing a lot of their properties, and there's a lot of interesting research that we can do on that area. So if you're interested, by no means, I'm happy to continue this conversation.
Definitely. Cool.
Great. Any final note from any of the speakers, if they wish, before we close? I think we are also running very beyond our initial schedule. Cool. Well, then I thank you all of our speakers. It's been a pleasure to have you in this symposium. And thanks also our attendees for their participation. And we should acknowledge also the WEISS Center and our communication manager, Annie Warnock, who supported us in the preparation of this workshop and coordinated all the speakers as well. And we do this work, this symposium on a regular basis. So if you want to know more about future events, please follow our Twitter page at WEISS_UCL, where you can be notified about this event. And thank you very much also, Lukas, for all the support with the organization and coordination with the event. And just a final reminder, the recording of this event, beside of the recording of the first part with Dr. Morris Becker is going to be available online and posted through our social network pages. So thank you very much. It's been a pleasure, and have a great week or day, please, on where you are.
Thanks a lot. Thanks for inviting
Thank you
us.
so much.
Thank you very much.
you.
Cheers. Have a good
Thank
day.
you.
Thank
That
you.
was fun.
Bye-bye.
Thank
Bye.
you.
Bye.
Goodbye.
Bye.
Bye.